Hello everybody, welcome back to our channels about chemistry again. Before the 2 weeks we talked about covalent bonds, now we are in a position to talk about something exceptional. But this exceptional thing is the whole chapter. We call it breaking the octet rules, okay? Remember the octet rules? 2 electron and 8 electron rules, okay? Now we tell you, okay, the octet rule is just general rules. Actually, are not of a molecule when they are forming, they have more than the octet rules, more than 8 outermost shell electrons. So first of all, remember how to count the outermost shell electron, because now it's not just 8, okay? Maybe different, okay? So count the original number of outermost shell electrons, okay? And plus number of bonds and plus number of dative bonds multiplied by 2, okay? And then by the octet rules, in the total number of outermost shell electrons should be 8. So before it's easier, we just trust this way. But now we tell you the world is big. Really big when you learn it before, only 8, 8, 8, 8, 8. Okay, now we can have more, really more. 10 is also okay, 12 is also okay. The world have expanded, so we talk about, we give it a good name, so not error, not exceptional, not deviate. We call it expanded octet of electron. It is happens so often that we call it expanded octet of electron. It can be more than 8, okay? And then expand the octet, the total number of outermost shell electrons is larger than 8. For example, SX4, for the S inside, it has 10 outermost shell electrons. And X is the hydrogen, okay? And they have a different shape, okay? Expanded octet for the central atom with a lot of different shape. Remember the electron domains concept. Remember the lone pair will repel other things more. So for this electron domain, we have a 4 electron domain thing, but it is expanded octet, okay? Bromium oxide, PrO3 minus, okay? And then it has a trigonal pyramid shape, okay? It's more than 8, okay? So the central one, you can count 1, 2, 3, 4, 5, 7, 8, 9, 10, 10. Wow. So the other thing can be similar to, for this one, that they have a 5 domains, okay? Electron domain, it can be a trigonal bipyramid. Yeah, it is 5 trigonal bipyramid. If it has no lone pair, all the 5 domain is visible. And then on the trigonal plane is 120 degree, and then up and down is 90 degree, okay? For example, pH 5, okay? Trigonal bipyramid, okay? Of course, sometimes it can be a lone pair, one of the electron domain. If it's a lone pair, remember lone pair repel more. So lone pair will appear where? 120 degree or 90 degree? Of course, 120 degree or more. So the lone pair will appear at the trigonal plane, okay? So for example, one lone pair. So what is remaining we can see is a straight, and then a seesaw shape, okay? And it is a SF4. If 2 electron domains are lone pair, it becomes 2 lone pair here, and you can see a T shape, okay? T shape. And how about if 3? Wow, all are lone pair in the trigonal plane, then it become linear. It is X field, so you can see it is a fairly fascinating idea. And of course, you can even more. It can be a 6 electron domain. We call it square bipyramid. No. We call it octahedral. Okay, the square bipyramid is a regular 8 faces 3D diagram, right? So we call it octahedral. Okay, octahedral basically that horizontal square plane and then 2 peaks up and down, okay? For example, SX6, okay, we have 6 electron domains, okay? How about if there's lone pair, where will it be? Okay, all are 90 degree, of course, up and down, okay? If it has lone pair, it will occupy the up and down. For example, ClX5, okay? If you occupy the down one, then you can just see the top one. This is the square pyramid. Square pyramid. If we have 2 lone pairs, just like in ClX4, okay? 2 lone pairs, so it will be a square plane, not trigonal plane. Very funny, okay? So what you need to do is first find out the number of lone pair of the central atom, okay? And then find out the number of electron domains of the central atom, okay? And then draw the structure out, and you can recognize whether it's 5 electron domains, 4, 6, or where it's the lone pair. Remember, the lone pair will have to place that is far away from the other. Formal charge. So formal charge is a concept very important. Okay, for the resonance structure, you have to use the formal charge to decide which resonance structure are more probable. The concept is for formal charge closer to zero, it is more probably likely to exist. Okay, so choose this one. Okay, with a formal charge closer to zero. What's the formal charge? One is a variable. Okay, calculate from each atom in the species and use to determine which possible Lewis structure is preferred. Remember, closer to zero is better, more easily to be observed, more probably to be observed. But then what's formal charge? Okay, it's a charge assuming the bonding electron are distributed evenly amongst the atom in the bond complete sharing. So how to calculate a formal charge? Very easy. So first count the number of atomic share of electrons in the neutral atom, okay, and then minus the number of electrons in the lone pair, and then minus the number of bonds, okay, and it is the formal charge, okay. And then we talk about the bond, okay. Sigma bond and pi bond is a very important topic, hybridization. We always appear in IBDP, and we have to talk about it now. Okay, it's a right position to think about it. What is a sigma bond? A sigma bond results in head-on, end-on, axial overlap, or orbital. Axial overlap. And how about the pi bond? It's a sideway, okay, parallel overlap. It's a pi bond is a result of sideway overlap of two parallel p orbital. Must be two p orbital, also sideway overlap. So you see the difference behind it. There are two kinds of covalent bonds, sigma and pi bond. Okay. Sigma bond a head-on combination. Okay, it can be SSSP or PP. Okay, but the pi bond must be PP and also must be lateral combination, side by side. Okay, so we will find out the rules very soon. Okay, and bond axis is the axis joining the two nuclei of the atom bond. Okay, for the sigma bond, the electron orbits overlap with the axis. Okay. And the pi bond, they also overlap, but not exactly on the bond axis. It's above or below the bond axis. Okay, it's like this. Okay, visualization is best. Okay, if it's SS orbits sigma bond like this, SP is like this, PP is like this. Okay, but about the pi bond is maybe PP sideways. Okay, up and down. Okay. So you find out. Okay, if it is a pi bond, it must be PP sideways. But when will a pi bond be observed? So it is the situation scenario. It's a double bond and triple bond. So look at here. This is SS sigma bond, SP sigma bond, PP sigma bond. It might be sigma bond. So when do we have the pi bond? Okay, so for the single bond must be sigma. For the double bond must be 1 pi and 1 sigma. For the triple bond must be 1 sigma and 2 pi. Yeah, the lateral one, the end to end, and the sideways one. So it is the rules of remember. Double bond, 1 pi 1 sigma, okay. Triple bond, 2 pi 1 sigma because of the lateral one, okay. Sigma 1. For the other single bond must be sigma, okay. This rules, okay. Just look at the rules again. Try to get the paper and draw it out, and you will learn it quickly. As an example, you can talk about the benzene, okay. The benzene, okay. Total number of sigma bonds, okay. Number of single bond, plus the number of double bond, plus the number of triple bond. All the bonds triple contribute 1, okay. To sigma bond. For the pi bond or double bond contribute 1 and triple bond contribute 2. Okay. So it is the distribution. Okay, you have to count it. For example, for the benzene ring. Okay, wow, single bond, 9 single bond and 3 double bond. So altogether sigma bond is 12, and altogether for the pi bond is 3. Okay, very funny thing. For hybridization is the other concept. Okay, for hybridization the S spin up and spin down must be promoted to the P, and then the hybridization will occur. Okay, but which one will be hybridized? It depends on are they the same type. Okay, if they're the same type or a sigma bond, they will hybridize. Okay, if they're a pi bond, no hybridization. Very easy. Remember, except for the p orbital electron forming by pi bond, it means that if it has a double bond, 1 less, it should be sp2. If we have 2 double bond, 2 less, it will be sp hybridization. So remember, pi bond can't hybridize because sigma bond hybridize together. Okay. Look at the example. For example, for this one is linear CO2. So you see a double bond. Okay. So only the one. Okay. So the other 2 is a pi bond. Okay. So it's sp hybridization for the carbon. For this one, BF3. Okay. So okay, all are single bonds. So all the 3 bonds are hybridized. So it's sp2 hybridization. And for this one, 4, you remember even the lone pair will hybridize, okay? So double bond, so -1, so it's sp2 hybridization. For this one also double bond, so sp2 hybridization. And tetrahedral, wow, 4 bonds, so svp hybridization, also svv, also spv. Remember, lone pair also hybridized. Okay. Only what can be hybridized? Pi bond. So think about if it is a carbon, okay, you can think about if or a single bond sp3, right? One double bond sp2. One triple bond or two double bond, okay, sp hybridization. And the other two is the pi bond. Okay, remember pi bond don't hybridize. That's the thing that's important to you to think about hybridization. Remember, pi bond don't hybridize. Double bond, one pi bond don't hybridize. Triple bond, two pi bond don't hybridize. Okay, and count the other. Got it? Well done. See you for next. Bye.